Welcome to lesson 36 of my DP chemistry curriculum. Today we're going to be going over structure 2.1.3, how ionic compounds exist as three-dimensional lattice structures represented by empirical formulas. And for that, we're going to be using formula units as we discussed in our last lesson. Furthermore, we'll explain the physical properties of ionic compounds a little bit, including volatility, electrical conductivity, and solubility. So we'll just be going over those just a little bit in this lesson. So, starting off with the strength and structure of ionic compounds, we learned a little bit that they form lattices. And that's because ionic bonds form between more than just the ions of the formula unit. So, what I mean by that is when we have Na and Cl, it is more than just one Na plus and one Cl minus, but they form this repeating structure. They create a lattice. So what is a lattice actually? Well, we have lattices in more than just ionic compounds. Lattices can be in metals, lattices can be in molecules, lattices can form anywhere. So let's go over what a lattice actually is. That is a 3D repeating structure of atoms, ions, or molecules uh, in a crystalline structure. I use structure twice. Let's remove one of those. Let's say a 3D repeating arrangement of atoms, ions, or molecules in a crystalline structure. So we can see what these look like. I downloaded a couple images online to insert here. So we can have a simple lattice like sodium chloride, which is just a 1-to-1 ratio. And I got these from a website called AmericanBobcat.blog, just to credit them. So we have our chloride and sodium, chloride, sodium, chloride, sodium, and they repeat in this pattern where we always have them touching each other in this simplified lattice structure. However, if we have something with like a polyatomic like chlorate, we can still get the same structure. And it looks a little different because we have these large polyatomic chlorate molecules going through, but it is still just a repeating lattice structure. We have these cations evenly spaced, and we have these anions also evenly spaced. And it doesn't really matter. Even when we have multiple cations and anions in a different ratio other than 1-to-1, we can still get a lattice structure. So what do we do with this information? Well, the first thing to talk about is this idea called lattice enthalpy. We're going to talk about enthalpy much later in our curriculum, but a way to think about enthalpy is just energy, or often thought of as heat energy, but we can just think of enthalpy as energy for now, and if you just replace that word with energy anytime you think about it, it will serve the same purpose. So the lattice enthalpy is the enthalpy or the energy change when 1 mole of solid uh, ionic lattice, solid ionic compound breaks down into gaseous ions. So what I mean by that is if we look at this image above, if we have 1 mole of this solid sodium chloride lattice just becoming chloride ions and sodium ions in gaseous state free floating, that would be the lattice enthalpy. So 1 mole of those separating. Now that means we have to break those bonds. We have to break the electrostatic interactions holding them together. So lattice enthalpy really is just a measure of the strength of the electrostatic, oops, electrostatic interactions between ions, which, for the record, the electrostatic interactions between ions is our ionic bonds. So if they have a very high lattice enthalpy, meaning it takes a lot of energy to break those bonds, then we say it's a strong ionic bond. So we can just reference this by saying, therefore, a high lattice enthalpy, whoops, enthalpy is the same as a strong ionic bond. A low lattice enthalpy is a weak ionic bond. So it's pretty easy to see that now if we were able to measure the actual energy it takes, we can figure out the strength of the ionic bond based on whether it's high or low. We can also go backwards. We can predict whether it has a high or low lattice enthalpy based on what we know about the ions. And because ionic bonds are nothing but electrostatic interactions, the thing that determines the strength of that bond is the same thing that determines the strength of the electrostatic interaction. So we can say lattice enthalpy is based on, on the same factors as electrostatic interactions. So those forces that hold charged particles, it's the same thing. So we could talk about ionic radius, so the size of the ions that make it up, which is just size. And we could also talk about ion charge, which is the magnitude of charge. So when we look at ionic radius, a small radius would equal a large force. So a large electrostatic force because the atoms are smaller or the ions are smaller, they can get closer together and therefore have a stronger attractive force than two very large ions. So that's kind of like if you take two magnets and you put them next to each other. So if we have, let's see, north, south, north, south versus this magnet. So this attractive force is going to be very strong. However, this attractive force is going to be very weak because this distance is much larger. So a larger distance is a weaker force. A smaller distance is a larger force. And so this is why ionic radius has such a large impact on electrostatic forces. Now, when we look at ion charge, the magnitude of the charge, we know a larger charge is equal to a stronger force. So now if we have a couple equidistant ions, we maybe have 1 plus and maybe a 4 plus, and we put a little 1 minus in the middle of this. And these distances are equal. We're going to feel a small attractive force here, but a much larger attractive force here because we have a higher charge. That 4 plus is going to pull on the 1 minus far greater. So a large charge makes a strong force and a small radius makes a large force. So to get a very strong lattice, we want a small radius and a large charge. So for example, aluminum fluoride, aluminum is 3 plus, fluoride is 1 minus, and fluoride is very small. is going to be stronger than something like potassium bromide, where these both have a 1 plus and 1 minus, and bromine is large and potassium is also large. So this would be a stronger bond. So the last thing I want to go over, or actually before we even go over that, let's just talk about a couple things. When we look at things like solubility, whether things dissolve, having a weaker lattice enthalpy would allow it to dissolve more. Volatility, when we talk about things becoming a gas, again, being we having a weaker lattice enthalpy will allow things to become a gas more easily. That's literally what lattice enthalpy is. So the stronger the force, the harder it is to remove those ions, and the weaker the force, the easier it is to remove those ions. So this is the end of the video, but what I'm going to do is just do a little aside on electrostatic forces. And I'm going to talk about it in the lens of physics, because they usually talk about this as the electric force. So in physics, they usually talk about the electric force, and they discuss it with an equation. The force is equal to K Q1 Q2 over R squared. F is going to be the force. K is just some constant, so we don't need to worry about it. Q1 and Q2 are charges, and they can be positive or negative. And R is the distance between charges. So we can see what things actually change the force. Force is dependent or is proportional to Q1. Force is also proportional to Q2. So if we change the charge, we change the force. Change charge, we change force. It's simple as that. We multiply a charge by 2, the force gets multiplied by 2. It's pretty straightforward. They're directly proportional. But here's where it gets interesting. Force is also proportional to the inverse squared of the distance. Therefore, if distance increases, force decreases a lot. Because it's inverse squared, if we double the radius, we are one-fourthing the force. This is what the inverse squared law states, which is what kind of describes anything or any force that is radial. Inverse squared law. So that's kind of what this is all based on. Any force that kind of is radial around a central object dissipates in terms of the inverse squared law. So the further away we get, the much more drastically low the force becomes. So when we talk about anything with electrostatic forces, this is why the distance or the size of the atom is always more important than the overall charge. It's more important to have a small atom than a large charge because size is affected by inverse squared. So that's my little aside on electrostatic forces. You didn't need to stay for this, but if you did, I hope it helps and have a great day.